Swayam Prabha. Digital India. Educated India.
Hello, welcome to this course on transport phenomena. We are on lecture 11. In the previous lecture, we talked about flow through packed bed and fluidizations, etc. As you may be observing, we are building up on what we developed in the beginning, that is overall mechanical energy balance, then friction factor. So far, we are building on those concepts and demonstrating how those can be applied to several examples, and those examples are very often very relevant to the industry and many scientific problems as well. In continuation to that, today we'll talk about a very special case, which is the compressible flow of gases. You know that gases can be compressed, and to start with, you can use ideal gas equations to see to see the compressibility effect. So if there is large change in pressure, then you can expect, and temperature, then you can expect that there has to be corresponding changes in density, so it can be compressed or expanded. Under those conditions, how you can calculate the gas flow rate or other behavior, what is the velocity, and so on. So we'll talk about these things today. Okay, so today we'll talk about compressible flow. Specifically, we'll talk about two cases. That is compressible flow through pipe of constant cross section. So if you have a pipe, it could be a constant cross section, it could be a network of pipes, etc. as well. So we'll talk about compressible flow through such a pipe that where cross section does not change. Right. So you see cross section is not length of the pipe. And then we'll talk about a very interesting aspect of compressible flow, that is flow through this converging diverging nozzle, also known as D-level nozzle, in memory of the person who developed it. So in this case, you will see that you start from what if you converge and then you diverge. So if you have a nozzle like that, how will you flow it? Okay. So this I'm sure you have seen this geometry at many places, and if not anywhere else, you can certainly remember a rocket launch, and so you will see that there's you are seeing a diverging section there. And when we discuss it, you will be able to connect why it is important. Okay, so with that, let us see some more examples of compressible flow. So if you have a reservoir somewhere, and from the reservoir you have a gas that you want to supply from this reservoir to some other place. Okay. So this could get at pressure P1, and then you have some furnace where you are, let us say, supplying oxygen. It could go to a burner, like, and so on. So from here P1 to it goes to somewhere. It could be network of pipe, as well as I was saying. It could be network of pipe. We have several turns and so on. With that, we have seen that we can handle such a problem by considering equivalent friction factor and so on. The work done by friction equivalent to turns and so on. We have seen it before. So if it goes to P1 to P2, P2 is your exit pressure, there could be compressibility effect, and you need to consider that. As I said, there could be in rocket engines. This is very prominent. You have a burner, and you have a section where you have this combustion happening, combustion area, and then you take those flue gases and then combustion gases, and then you pass it through a nozzle like this, and then you expand it. That is how your rocket looks like. this this will further you have actually space shuttle it could be carrying. But this is what this is what happens here. You have combustion, and all the gases gases product of the combustion actually goes through this section, and you will see why this section is very important. Why there could be gas injection in liquid metal processing. For example, if you are aware of steel making, in BOF, we have oxygen injection, and that lens has to be it has to have the supersonic flow. So we'll see how we can go to supersonic, and you may not know what is supersonic, so we'll talk about that as well. So certainly the compressibility effect is very much there, and then it's very important to understand how that works. Okay. So before we do that, in general, if you have a flow through such a long tube, it could be flow through just a small nozzle. So typically, the actual process may not be actually may not be perfectly adiabatic or perfectly isothermal. But as a rule of thumb, if you have a flow through short section, such that for example, it could be nozzle, a small pipe, etc. So if that is the case, then you consider that as adiabatic process, because if it is very small section, then there is not much surface area available for so that it can interact with the surrounding. So overall heat exchange of this fluid to this outside atmosphere is small. So we can consider this as adiabatic. In contrast to that, if you have a very long section with kilometers, it could be several meters and so on. Then you have to consider this as isothermal, because fluid and inside flowing inside will interact with the atmosphere, and there would be certainly energy exchange, and to an extent that you can assume that the temperature does not change as much. So you could consider these are isothermal, and this as if it is through small sections or nodules, you can consider that as adiabatic. Okay. So this keep in mind. Okay. So now we'll start with flow through state pipe, and then the pipe has uniform cross-section area. Okay, area. Okay, so you have some conditions here. P1 rho is the density, and P is temperature, and here you have some P2. Here could be velocity, could be V1. Here velocity could be V2. Okay. So first of all, if you look at mass conservation, or from there you get the continuity equation. So mass flow rate m dot would be written as rho a p. So this is and this is constant. So wherever you take rho 1 a1 v1 has to be equal to rho. Okay. Since a1 is equal to a2, so we can say that m dot by a is also constant. So this is rho 1 v1, and it could be any other place. Also you could have rho v. So you can say rho v. Okay. So this quantity, you see mass flow rate per unit area. So mass flow per unit area per unit time is given, can be called as mass flux. Okay. So mass flux is we generally denote by G. So G is rho times V. Okay. Typically what you do is you define what is known as specific volume. Specific volume is nothing but volume per unit mass. So volume by mass. So it is essentially 1 by rho. Okay, so if you use this here, you can write V as G by rho, or G times a specific volume, which is denoted by V cap. Okay, so V hat is your specific volume. So this is one. Listen, this comes from continuity equation, and we use it. So please note that G is constant because you have constant cross section area. So G throughout this length is constant. Okay. Okay, so as usual, once we have done the continuity equation, we'll do the overall energy balance. So if you recall, I've removed the soft work here, but this is your kinetic energy term. This is your potential energy term. This is work by the flow, or by pressure, and then this is friction work done per meter mass by friction. So now since rho is not constant, we are assuming compressible flow. And as you would recall, typically when we say compressible flow, this means Mach greater than 0.3. We'll come to that. So rho is not constant. So we need to know there has to be some relationship between P and rho to do this calculation. So it will be better if we can write this in differential form. So in differential form, this can be written as V dV plus G dz plus this will be just dP by rho. And then EF, EF is what? 2L by D. And then you have V squared FF. Okay. And from previous slide, we know V squared is G times V. So we can write as 2 G V cap squared FF by D, and when you write in differential form, we will write it DL. So here the assumption is that friction factor is independent of velocity, and which is true, because at very high Reynolds number, the curve is flat, horizontally flat, so it doesn't change much with Reynolds number. So it's independent of Reynolds number. Okay, it does depend on surface roughness, however. So what we can write here is 2G V cap squared by D F. Okay, right. So now what we can do is, let's say it is horizontal, so we just get rid of this term. So okay. Now VdV also, we can write, since we know that G is velocity is G times V cap. So if you do dV, G is constant, so this will be dV. So V dV will be V times this, V is this, and then you multiply these two, so this will become G squared V cap dV. Okay, and this is as it is, dP by rho plus 2G V squared by D F dL. It's 0. So now we can divide everything by V square, so that at least this term becomes just dependent on L, not anything else. So if we do that, then this will be G squared dV by V plus this 1 by rho, we could write 1 by rho as just V, because that is how we define a specific value, specific volume. So 1 by rho is V. So now when you divide by V squared, this will be dP by V cap, and this term is independent. So 2G V squared is gone, so that should not be there. 2GFF by D times DL equals 0. So now we want to integrate all of this, and we want to find what should be our G squared. Because G squared is constant. Other things, if you integrate and put it other side, you can find what will be your G squared given your change in pressure and density, etc. Okay. So to do that integration, we need, main hurdle is integrating this term is easy. This integration will be just L. We have considered FF to be independent of velocity, so that way this is constant. So main, if we can find a relation between P as function of V, then we can integrate it easily. Or so to say, if we can find P as function of density, then we can integrate it easily. Okay. So to start with, we know that Pm is equal to rho RT. This is for gas. Okay. So if it was the isothermal process, then T is constant. So P1 by P2 equals to 1 by rho 2. If it was isothermal. Okay. On the other hand, if it is adiabatic, then PV gamma is constant, where in this case V is the volume. So you can also write this term as PV. Gamma is also constant, because if you multiply it by molecular weight, rather multiply by molecular weight, etc., it will be the same thing. Okay. Yeah. So now we can use this to actually evaluate each term. So the first term that you want to do is dV by. So we have two integrations that we want to do this, and then you have other one is dV by. So we want to evaluate these two equations. So this one is direct. This will be ln v2 1, and this is equal to ln rho 1 by rho 2. So from here, this you can alternatively write as P 1 by rho raised to gamma is constant. So P rho minus gamma is constant. So if so from here you can actually evaluate this term. Okay, it's ratio, so constant will cancel out. To evaluate this term, again you can use this equation. You can use this equation. So when you substitute here and you can do this integration, so v bar will be some constant by p raised to 1 by gamma, and when you substitute it here, so you can integrate and do all the calculations. The only thing that you need to take into account is C could be anything. It could be P1 V1 gamma, P2 V2, whatever, any PV. So that way, if you know the entry condition or exit condition, you can find this thing, and you can see that effect comes here. So I'm not going to do the integration. It's a little tedious, but I think you should do it to convince yourself. But this is a solution. It's a little complicated equation, but if you know if you know your entry condition P1 rho 1, and if you know your exit condition P2, and if you know where gamma is your for Cp by Cv, so if you know gamma, then you can find what will be your flow rate, depending on what is your friction factor, what is your L and D. I mean, again, this ratio P2 by P1 is given. Okay. So from here you can find the g square, which is mass flux. So that will be kg per meter square second. Okay. So this is how you do it for if it is adiabatic condition. Similar calculation could be derivation could be done for isothermal condition. Okay, over here it should be actually g square, all this term, because we're replacing this v is equal to g v cap, so it should be g square v cap square instead of g. Okay, so that is the equation you have to solve. So 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 before showing that, let us see what is the meaning of this plot. Okay, so what I have done is essentially plotted this g square versus T2. So if you have a given pipe, as I said, maybe it may be coming from some reservoir, which is at pressure P1, and then it is going somewhere at pressure P2. Okay. So there could be some entry and some exit conditions. So if you know you already know that P2 has to be less than P1. So if you could if you start in this case, for example, we start with P2 equals P1, so there will be no flow because the pressure is same. So G 0. If you do P2 equals P1 here, this will be 1, so everything will become 0. Okay, so you start from here. Now, as you are reducing pressure, as expected, the gas flow rate will increase. Gas flow rate will increase, and what it shows is it goes through some maximum. And if you further decrease the gas pressure, then the flow rate decreases, which is physically possible. This physically is not possible, although all the mathematics say that it's not possible. It physically does not make sense that flow rates should decrease. So what happens is essentially you get some maximum velocity. After that, no matter how much you decrease the pressure, you will not see any change in flow rate. So it becomes something else. Okay. What happens with and this also you can verify. So this also you can verify when if you calculate the velocity corresponding to this, you will find that this is equal to gamma RT by m, where gamma RT by m is actually a speed of sound under adiabatic conditions. So what happens is if you have this section, you have some fixed pressure here. You are reducing this pressure. So when you're reducing this pressure, the information of this reduction in pressure travels to the medium, through the medium via via sound wave. So if your flow rate reaches sonic somewhere, then any change in pressure at this point will not be communicated to this. So it cannot ask for more and more gas to come. So flow becomes what we call here as becomes choked. So after that, no matter how much pressure you decrease, there cannot be further flow. Okay. Uh, it is called choked flow. Okay. You should note that this temperature it has to be the local temperature. So wherever it is choked, so if it is choked, since it's likely to get choked here, uh, it has to become R2 by M. Okay, so it has to be T2. Okay. It has to be at the exit. Okay, so it is so you can say that here this gamma RT by M maybe something else. T1 by M is something else. Here it is something else. So it's likely to be choked here, and you can do some thinking on why it will be choked here. Okay. So this gives you the maximum fluid velocity. Okay, and then g square is maximum here. So this gives you the maximum flow rate that you can get. So if you have a straight pipe, then you are actually limited on how much gas you can pass through it, because your g square is limited. You cannot go any further up. So this is your limit. That is how much gas you can flow, unless you change some conditions where you have some larger temperature, or so that your sonic velocity is larger. Okay. So typically what happens is, so this is your flow is sonic here. So here you call it subsonic. If it could go beyond this Mach 1, then you call it supersonic. That we'll discuss in a little bit. Okay. So similar derivation, as I said, could be done for isothermal condition, and then again, if you know P1, P2, and if you can calculate friction factor, length and the tube. Initial conditions you have to know. So if you know all these things, then you can find G square. Initial condition, I mean the inlet condition. Subsequent, the other way around, if you need outlet condition also, then also you can find it, because Pm equals rho RT in this case. So M by RT, 1 M by RT is P by rho. So it could be, this is constant. So if you know inlet, or P1 by rho 1 or P2 by rho 2, you can find it. At least one of them you should know. Okay. So this is how you can calculate the flow rate. So let me just give you more idea on how you can use these two equations. So first is, if you want to know mass flux, and if you already know P1 rho 1 T1 or P2 rho 2 T2, either way is fine. But you have, on the other side, you have to know at least one. So pressure, then it is straightforward. Then you can calculate the mass flux rate, G squared. However, you have to make sure that the flow is subsonic, because you could be, if you calculate G squared, you could be on this side of the graph, and if you are here, your test is such that if you are here, then you are calculating the flow rate wrong. It should be either actually this. Okay, so you have to make sure that you are on this side. Okay. And how do you do that? You actually calculate the velocity here, and make sure that it's subsonic or max sonic, not supersonic. Okay. So just calculating G squared may not be enough. You have to actually do the velocity as well. And to calculate velocity, you calculate V. V is G times 1 G by rho. It should be G by rho, right? Okay. So V should be G times G by rho. Okay. So once you know G, you again need to calculate rho. Rho you can calculate from, again, depending on if the gas is, if the condition is isothermal or adiabatic, it could be PV gamma is constant, or P by rho is constant, right? So this is the case when you have adiabatic flow. This is the case when you have isothermal flow. So you can, either of these you can use, and find velocity. Okay, and you have to make sure that this is subsonic regime to use it. Okay, so with that, let us do a very simple practice problem. So consider flow through a short section of pipe. Short section, you not the word. So the inlet and outlet conditions are given to you: P1 rho 1 T1 and P2 rho 2 T2. If flow is choked, it's already given that it is choked. What should be the maximum velocity? No, I'm assuming that there's no other combustion or anything happening. So whatever change in temperature is because of compressibility effect, not due to any chemical reactions, or combustion or anything else. Okay. Of course, there is some changes in due to friction as well. But let us say that change is not very appreciable compared to what is the change, compared to the change because of compressibility effect. Okay. So what should be your maximum velocity of gases? Should it be should you calculate with respect to this, or with respect to this, or you should take an average, or you should take a subtract and based on the discussion, you should be able to. After doing this problem, let us move to this flow through converging diverging nozzle. And we study that because in many cases we actually want to have this supersonic flow, and we saw that in straight tube or straight nozzle you can also have. You cannot go MA has to be less than equal to 1. You can't go beyond Mach 1. So Mach is defined as whatever is your current velocity by this A, what A is your velocity of sound. Okay, and we saw that for adiabatic condition you can have this as M. Okay. So converging diverging nozzle, what do we mean by that? First of all, let's see that. So what you have is essentially you have one converging section. So you start from here and you converge it. Try to converge it. Okay. And then you have what we call as throat, and then you have diverging. You will generally see that the converging section is the gradient of it reaches your throat very fast. So the reduction in area is much faster compared to expansion in area, and that has to do with boundary layer separation, etc. Not get into that, but this is just for information that this you will see that strong gradient here. So this is your converging section. This is your diverging section. And this is known as throat. Okay. So the gases can come from a reservoir over here. No, it could come from reservoir here, and it can even end in a reservoir there. So those kind of things are possible. Anyway, so you can call it reservoir 1. So this is just to limit, mention, this is the, from here 1 to 2. This is our region of interest. Okay, we want to know how the fluid flow, characteristic of fluid flow in this region. So 1, then you have throat, and then 2. Okay. So in this nozzle, we can write a continuity equation similarly to what we need for do for all flow. So essentially, continuity equation comes from your mass balance. So what we can say at any place the rho AV is constant. You can think that the area is no longer constant. So you have to keep the area. So if I write this in differential form, you can have rho A dV plus rho DAV dA V plus rho A D rho and D rho AV. Okay, this is equal to 0. If you divide everything by rho AV, then you will have dV by V plus dA by A 0. Okay. So this we are not going to get into derivation, but if one does energy balance through a moving sound wave, one can show that the velocity of sound can be written as del P by del rho for S, whereas constant S, which essentially means is entropic process. So for constant entropy condition, we can write for. So we'll take this as granted. So now let us move to mechanical energy balance. So we neglect the gravity term, and since this nozzle is so small, we can also neglect the friction term. The loss due to friction may not be as much. So if we do that in the differential form, we can write this as dP by rho. go to what we did earlier. This one. So in this, we are neglecting this as well. So you have only these two terms remaining. So you will have dp by rho plus v dv is equal to 0. Okay. So if you could integrate this equation, then you can find your change in velocity, etc. Okay. So one can do that. We'll come back to that later. Here we first thing we want to do is we want to relate this change in cross sectional area. That is the main thing that happens in the nozzle. As far as nozzle design is concerned, that is the main thing. How does your area changes along the length. Okay, we call it dA by dx or whatever. So we'll first we'd first like to see how that area affects our flow. Okay, so dp by rho. So let us start with this term. So we call it dp, and we can have d rho times d rho. Okay, so dp by d rho, I said that we'll use this equation. So that means this is a square. So this you can write as a square d rho. So from this analysis, we can write a square d rho by rho is equal to minus p dv. So d rho by rho, what we can write is as minus p by a square dv. So if we multiply and divide this by v, what we can write is v squared by a squared is essentially Mach. So this is minus m squared by v. Okay. And from this equation here, so we already know d rho by rho can be written as dv by v plus dA by a with minus sign. So we can write this as minus dv by v minus dA by a is equal to minus m squared dv by v. So you can cancel all of this. So dA by a, hence dA by a is equal to m square minus 1 m square minus 1 dv by v. Okay. Right. Yep. So we'll see what this means. Okay, so roughly we know that depending on m, we can tell the sign of if m is greater than 1, less than 1, and so on. Let us get into that. So let us first say that your m, and you should recall that this m is v by a, where v and a are your local velocity and local sonic velocity, because a also changes with temperature. So if your temperature is density changing, pressure is changing, temperature is changing. So your A may also change locally. So this is very important that you consider. M is not a constant. Okay. So let us see the condition when you have first let us say if M is equal to 0. If M is equal to 0, then dA. So then what you can see is you can write dA by A plus dV by B equals 0, which essentially means that A times B is constant. So this is your continuity equation for incompressible flow. And we have seen that when Mach number is very small, we put the limit on less than 0.3. We can consider this as incompressible flow. So all these discussions we have already done. Now, second subsonic condition will be m is more than 0, but it's less than 1. Okay. So if that is the case, then we will see what, let us see what happens. So if this is your nozzle, this is your nozzle, this is the throat. Um, so if Mach number is between 0 and 1, let me, I'll just rewrite this equation here. So what we have is dA by A is equal to m square minus 1, right? M square minus 1 dB by. So if Mach is less than 1, then what you see is as area goes down, so dA is minus, this number is less than 1, so this whole thing is negative. So as area becomes smaller, velocity will be large. So let us plot. If we plot velocity, or you could plot this as velocity, or v by a, or Mach with respect to Mach number. But let us say velocity, how it will change with respect to x. So as area is going down, velocity will go up. This is your, okay. And then what will happen? Now your area is becoming larger, so this will become, right. It's a schematic plot. Okay, so this is through. So similarly, what will happen to pressure? Or you typically plot this as P by P naught, where P naught is the condition here. Okay, and P is at any location. Okay, so so we know in this case we haven't considered any frictional losses, etc. So P by P plus half rho V square is constant. This is what roughly you can write that. So so what will happen? The pressure will, of course, initially will go down, because you're increasing the velocity, and after this point you're reducing the velocity goes down, so pressure will go up. Okay. Similarly, you can keep increasing the velocity, and it will do the same. Pressure will go further down. So you can also think of situation where you have, this is P naught, and this P, initially you had P naught, and then you are slowly reducing it, and when P naught is small, is P1, it becomes P2, much smaller. Then you will have this kind of pressure profile and so on. So this will keep increasing till your this thing becomes 1. Okay. So when Mach is 1, so it will become choked here. And so after that, now if you look, now if you go further, if you have condition where Mach is greater than 1, then this is positive. So what does it say? dA and sine they have the same signs. If your area increases, then your velocity will also increase. So once you have reached the sonic, if your Mach is greater than 1, slightly you want to push more gas, so then this region will become supersonic. So we'll look at that aspect in a little more detail. Okay. So you can have a supersonic condition when your Mach is greater than 1, and we see that in diverging section, velocity will increase. Keep increasing. Okay. So for that, you can actually integrate this and come up with solutions. Integrating this part is simple. It's just V squared by 2. To integrate this, since this nozzle is small, we can consider this as adiabatic. And we have seen how to integrate if it is adiabatic. So we know to you don't have to do it from 1 to 2. It can be 1 to any point x or whatever. P naught to P. And since we already know that P rho minus gamma is constant, So from here you can integrate this, and integration will we will if you do that integration, you will get this result where any local velocity can be given as 2 times using this equation, where P naught is your entry pressure and P is the local pressure, and this gives you the local Mach number. So V squared by M, M squared rather, M is gamma RT by M, which is essentially same as gamma P by rho. So from here you can once you know that, you can write this question in terms of M squared as well, and you can rearrange to find the P by P naught as well. So in this case, now when your Mach number is 1 and above, what you can do is again you can go and think what will be your gas velocity and so on. Okay. So let us see. Let us see. You have some initial pressure P naught here, and we have seen initially what happens if you are in subsonic regime. Okay, and you have some pressure P, which P is also the local pressure. Some pressure, exit pressure, you have PE, and you start reducing the pressure. You will initially have some subsonic velocity everywhere, as we have seen earlier. Now, if you have reached to a point, where you have a choked flow at the throat, then let us see what will happen. So if you have Mach equals 1, you can see so you can also use this continuity equation to actually find, once you know V. Sorry, this will be V. Once you know the equation for V, you can actually find the equation for change in area as well, and find the relationship between area and velocity. That can be also done. But let us see here qualitatively what it will happen. So in the converging section, your flow is subsonic. So you start with no flow in there. But then as you reach here, your Mach is 1. Now you go to diverging section. Since the area is increasing, your velocity will keep increasing. So you keep Mach. Okay. So there is no trend like this. Your Mach does not have to decrease, as per this equation, right? Because in diverging section, now as area increases, your velocity also increases. Correspondingly, if you look at pressure, so pressure is now local pressure can be given by this equation. So if you look at pressure, initially you have your pressure will of course, as you have this, it will decrease. But if you look at this equation, if your Mach is this is valid. In the region here, you have Mach greater than 1 now, right? Mach greater than 1. Here you have Mach less than 1. So you can use this equation to plot the pressure variation throughout the nozzle. So you can see that P by P naught, it will start from initially 1, and as you go, it will actually keep decreasing. So you have equation, you can plot it. Okay, so this equation actually gives you the pressure variation. That will be there. Okay. However, if your exit pressure is not here, sometimes if you maintain this exit pressure, this is what question says. If you have if your Mach number is less than 1 here, greater than 1, then the pressure variation should be like this. But exit pressure may not be the same. In such cases, what happens is here you have this one, this is supersonic regime. In such cases, what you have is if your exit pressure is somewhere here, then there will be some shock formation somewhere, and then that will make this, so that the exit pressure becomes equal to this. So from here to here, then it will become subsonic. Okay. However, if you could maintain this pressure or below this, it will follow this law. Okay. So there may be cases where your exit pressure is not valid, is not equivalent to what you expect from this equation. Then there will be something called shock formation, which we are not discussing lecture. So shock formation is there. Essentially, shock formation, what it does is there is a huge dissipation of energy, and that changes your condition from supersonic to subsonic. If there was no shock formation, then this could be then this will follow this path, and it will remain supersonic. So then you will have supersonic jet that will go. Okay. So it is function of a P. Okay. So you could have, in this case, you could have Mach 2 or Mach 3 or whatever. So I hope this is clear. I'll just let me again, especially the pressure part. You can look at it, alternatively. You can look at it the case when, overall also, overall we can look at it this way. Okay. So overall, let us say you start with this P naught. You have some exit pressure PE. I'm just combining both so that you can get the complete. So initially, when initially, let's say you have P naught equals P naught. So there is no flow, right? There's no flow. Mac, and let's say P by P. Okay. There is no flow, and it is everywhere. Okay. So P initially, that is your case one. Okay. Now if you reduce the flows a little bit, then you will have some velocity. It will keep increasing till here, because we can relook at this. So in this case, as your area is reducing, velocity is increasing, but now your area is increasing, so your velocity will increase. Okay. What will happen to this? Since this here velocity is increasing, so this will decrease, and it will increase. Okay, but this is slightly less than 1. So if you keep increasing, this will go up. So let's say this and this will certainly go down, but you are still not at Mach 1. Okay. So this is your first case, second case, third case. You have first case, second case. You have increasing velocity. Now you have increased velocity such that you are at Mach 1, and then you have you are more gas, so you are going to Mach greater than 1. So then this will keep increasing. What will happen to pressure? Pressure will be no, it will go like this. However, if your exit pressure is still here, this is, let's say, 4, then what will happen is this is coming from the equation given here, but your pressure is slightly higher than this. So what will happen is somewhere here there will be shock formation, and then exit flow will be subsonic. Across the shock, it changes from supersonic to subsonic. However, if you maintain your pressure here, then it will just follow this, and your exit flow will remain supersonic. Okay. Under case 4, this is your Mach 1. So everywhere you have Mach greater than 1. But if you have shock formation, this Mach will be less than 1. But if you maintain this, then your Mach will remain greater than 1. It will rather keep increasing. Okay. So this is the main takeaway. There are some equations here as well, but if you could understand this qualitatively, that is also enough at this stage. You can calculate, for example, use this equation to, if you decide Mach numbers 4, 3, then you can find what should be your P by P naught. So if you know your reservoir pressure, what should be your exit pressure, and exit pressure you can control that. Sometimes you don't have control. If it is if it is in atmosphere, then it is whatever it is. Then you can only change this pressure. Okay. So with that, I hope I could introduce to you at least the compressible flow. Compressible flow in itself is a a large subject area, and it could just be a course. And if you look at aerospace engineers and so on, the entire missiles or rockets or space engines and all those things are even our jet engines are based on this. So this is very very important topic even from the process point of view. In steel industry, for example, we use supersonic nozzles to so that we can uh, we can do the BOF operation very quickly, and so on. So even in the process side, it is manufacturing processes. For example, in gas atomization for metal powder, the compressible flows are supersonic jets are very important. The shock formations, etc., actually help in forming final powder particle, which is very important for upcoming technologies such as 3D printing and so on. You want final powder with very good size control and so on. So this is very important area even for metallurgists and material scientists. So and it is exciting to it's not very intuitive to see how it works, but once you start learning about it, it becomes more and more interesting. Okay. So with that, let us do some practice problems. So in a CD nozzle, if flow is subsonic everywhere, then what you can say, Mach is maximum at the throat, Mach is minimum at the throat, or Mach is maximum in the diverging section, or Mach is minimum in the converging section. Uh, and then the last question is in the same similar nozzle, if you have a supersonic flow uh, in the diverging section, of course you cannot have supersonic flow in the converging section. So what can you say? Mach is maximum in the diverging section. Mach at the exit may be subsonic. If option B is correct, there must be shock formation. If option B is not correct, the pressure continuously decreases from inlet to outlet. So what can you say? It may be more than one option may be correct. Okay. So based on the discussion we just had, you should be able to answer this. With that, thank you for your attention. This is end of compressible flow. We will have maybe some more thing on next class. We'll talk about Navier-Stokes equation. We'll again limit our understanding to the development of equation, and at this stage we may not have we will not have time to see the applications, but in heat flow part we will certainly see some applications as well.